The more you work with networking, the more you're going to come to learn that every advantage comes normally at some type of disadvantage. Now, one of the things I want to talk about is what happened when we did the spanning tree election. We created that loop-free graph. So what I chose to do is I decided to just go ahead and redraw everything because I really need the real estate. So looking at this from the perspective of the 4 switches that we discussed, we know that we elect one of these devices to become the root bridge. And then what we're going to do is we're going to elect the least cost paths necessary to reach the root bridge, and we will call those the root ports. So we have the root ports and the root ports. Now the scenario here is it's important to keep in mind that we still have other links in the topology. However, they're not currently in use because what we're going to find is they're going to be blocking information. So we may use them to communicate out. As an example, one may be a designated port, but to prevent this idea of a loop, what's going to end up happening is that we will, again, like we had iterated before, we may be blocking these links. But if we looked at this, that means in this topology I have 6 links. So let's say I have 6 overall connections. So I have 6 links in the configuration, and the 6 links that I have, let's just pretend that they're all 10 gigabit Ethernet connections. Now that means mathematically here, in my topology, I have a total of 60 gigabits of throughput by taking all of those interfaces and adding them up. But the problem is, spanning tree protocol, for fear of creating a loop, is actually going to block, in this specific topology, it's going to block 3 of those. So by blocking 3 of those, what that's going to do is that's going to subtract a total of 30 gigabits of throughput from my overall capability, thus leaving me a total throughput of 30 gigabits. And that's only going to be individual links of 10 gigs. So when we start looking at this, as we said, these were all designated ports because designated ports lead away from the root bridge. But ultimately, the object here is to note that I only have these interfaces that are functioning in my topology because spanning tree shuts them down. Now let's go ahead and highlight another problem that we run into. Now let me rephrase that. It doesn't shut them down. It's blocking the data. Meaning that if this link right here were to fail, what would end up happening is my topology would ultimately take one of these interfaces out of the blocking state, and what it would do is it would ultimately self-heal. So again, this is what I refer to as reconvergence. Now, reconvergence is an interesting scenario because while I am reconverging, what happens is I can't forward data. So this becomes very, very problematic for us. And it also is going to take time to actually reconverge. So during reconvergence or a reconvergence event or something called a topology change, it's important to keep in mind that I can't forward data until such time that I've actually recomputed my loop-free graph. Now, this is made even worse when you take into account that a lot of organizations want more throughput. So as an example, let's say that I have a topology like so. And let's say we're dual connected like this. So I have 2 10 gigabit connections. So now in this scenario, I have 60 gig actual, and if I were to have a scenario like this over here, what would end up happening is I would have another 60 gigs sitting fallow. So we can see here I would have 120 gigs total throughput, but after spanning tree has its say, I'm going to be down to 60 gigabits of throughput, or at least on first blush. It's actually worse than that. What we're going to find here is it's going to take me down to 30. Now here's why. Keep in mind that as I advertise information, let's pretend this is my root bridge. And let's say I send information out. So this is going to be a broadcast. and it would be flooded. Well, the problem with that is as that enters into this switch, let's just say SW2, what's going to end up happening is the rule says that you do not send it out the interface that it arrived on. However, it didn't come in on this interface, so I can hairpin it and send it directly back, this giving me the possibility of generating a loop in my topology. So what's going to end up happening here is that we want to create a mechanism whereby we're going to shut down these alternate links in order to be able to prevent the generation of this loop. Now, this is, again, very, very problematic. So if we were to come in here and take a look at it and pretend that I had double connections for each one of these sessions, what we're going to find is that I would have 12 connections equaling 120 gigabits of throughput, but at the end of the day, Spanning Tree is going to take this and it's going to whittle it down to a scant 30 gigabits of Ethernet, because the only thing it's going to allow is one single member interface. And this has been a problem for us in data centers since the very, very inception, which is one of the reasons that they introduced technologies, one of which we'll be talking about in DCICT, which is Fabric Path, which is Cisco's proprietary version of another protocol called TRIL, transparent interconnection of lots of links, that actually gets rid of Spanning Tree and replaces it with an internal protocol that can actually do equal cost multipathing. Right now, as a direct result of Spanning Tree protocol, we cannot do equal cost multipathing. So we can't do load balancing in an automatic process. I could selectively pick a particular switch to be the root bridge for a subset of VLANs and thus create a topology that's going to allow me to leverage it, but that would be an administrative load balancing. When it comes to Spanning Tree, there is no concept of dynamic equal cost multipathing or load balancing. So these are very important concepts for us to keep track of. However, there is an answer to this solution, and we're going to entertain that in the next video, and that's going to be where we start looking at port channels. I'm Terry Vinson, and I'd like to thank you for learning Data Center with me.